Hello everyone, my name is Charlie and I'm going to be doing a basic tutorial on Openfoam. Now if you're a new user, there's definitely a bunch of resources on how to download Openfoam. It's open source, so pretty much anyone can get it, doesn't cost anything. And we're going to be going over one of the tutorials that comes with the package. Now when you download Openfoam, you get a whole folder of tutorials. Now what I'm going to be going over is just one of the tutorials, but also I'm going to change up things in the tutorial, do different things, show you different stuff that usually, if you saw online, it's different. So this is going to be slightly different from the tutorials that you can maybe see online because I'll be changing it up a bit. But just to start, to show this, you're going to have, when you download it, you have a folder. It's called Blue CFD for me. It might be different for you. It depends because I'm on a Windows. I'm basically just running Openfoam on Windows. Usually you can get a different operating system called Ubuntu to run it, but I'm going to be doing Windows. So if I go into this is basically the folder for how Openfoam works, all the code that it needs. But I'm going to go into these folders, so Openfoam 5x and the main folder, which is tutorials. Now, no matter what version of Openfoam you have, you're going to have a tutorials folder, and basically they are all the same. So if you want to kind of follow along with me and try to understand what I'm doing, I'm going to be going into the incompressible, and then I'm going to be doing pimple foam and laminar, so laminar flow, and planar contraction. So that's how I started at first, what I was, because always for Openfoam, it's always good to start from something that works, change little things, and move on from there. So I'm going to start with planar contraction, but I have my own folder now. So I'm calling mine flow contraction. So I've been working on it, and I have a bunch of different versions that show different stuff. So we're going to start with basically, I guess, what is Openfoam? Openfoam is a computational fluid dynamics tool to model flows. It can be internal, external, and there are many different filters, as they're called, to kind of understand the data. So for us, we're going to be using Pimple, which is a specific Pimple foam, which is a specific solver. And it is for incompressible flow, and it is for, it's using basically the simple solver, which a lot of people are well aware of, but it's also incorporating PISA, which is a different solver. So a lot of CFD, they use different solvers as basic core ones, and you can mix them up because they all have different strengths and weaknesses. So Pimple foam we're going to be using because it's a large time step transient solver. So to basically go into, I guess, the basics, if this is for any new user, when you enter any kind of folder, first of all, Openfoam uses folders, so it's not really a huge UI. I'll get to the UI part where it's a user interface where you can kind of click on stuff just like SolidWorks or those kind of softwares. But you start with just folders. Folders, files, and basically just WordPads, notepads. So with any basic Openfoam folder, there's zero, which, there's three folders: zero, constant, and system. Zero houses pretty much the initial time equals zero parameters, the constants. So what happens at time equals zero? And we're going to go in a little more in depth in all these. Constant, just constant properties. So transfer properties, turbulence properties. If you've taken a fluids course, a fluid dynamics course in college, or maybe you're just touching upon it and just trying to learn on your own, there are some difficult, I guess, concepts that Openfoam uses, and you have to know to learn, use it. But don't be scared off. It's not too hard. But if you want to learn more into what I'm going to be talking about, just definitely do a quick Google search and figure it out on your own. I'm not going to explain everything. System. So in the system folder, there's the block mesh dict, and all these folder names are going to become pretty familiar to you because they're very constant, which basically goes over the geometry, how things are defined, where are the walls, where are the inlets, where are the outlets. Control dictionary, which pretty much controls the simulation, time start, time end, when you're collecting data, how do you want that data to come out. Schemes and solution kind of work together, so it basically says how you're going to solve it, how close do you want to solve it, how precise do you want it to be, and there's obviously strengths and weaknesses in picking these parameters in these folders. So first I'm going to go into the constant, actually not the constant folder, I want to go into the system folder and talk about this. So we're going to do a contraction, a flow contraction. So it's basically going to start with a flow, a rectangular flow coming in and then contracting to a smaller flow. So obviously a basic concept is flow, which is A times V equals A times V. If it's a smaller cross section, speed has to go faster, continuity of mass. So let's go into block mesh dict, and I'll show you right here. So with every Openfoam folder, there is a header. This is just, you don't have to worry about it, it's just how it looks, and Openfoam has it. I'm not sure if you can delete it, but it kind of looks nice. So at the beginning, there's always a little just defining things. So this is a dictionary, block mesh, and block mesh dictionary houses geometry. So for ours, we're going to have a certain amount of vertices, in our case 16. And I would like to go a little bit into the basics of how this works. What this really is doing is it is drawing, I'm not sure if you're going to be able to see this, I'm pretty much drawing that. So it's going to have different vertices, and you can see that there's 4, 5, 6, 7, 8 vertices, and then there's also, it's going to be three-dimensional, so you're going to have 8 more that's on a different z. So here all these are -1, -1, -1, all these are 1s, and all the x and y values are the same. So we're basically making 2 big squares, one taller, one shorter, and we're just going to see that contraction, how flow gets down there and goes faster. So blocks are pretty much used to define certain sections of the geometry. Here I'm going to have 3 blocks, and this can get kind of confusing for a beginner. If you look at this picture that I showed you, it kind of looks like there's 2, like I want 2 blocks, right? A big one and a small one, big one. But actually I'm going to be doing 3 blocks. So I'm going to have this top rectangle end at right here, this smaller rectangle that matches the small one here, so it's going to be 3 blocks. And I'll get to, you'll kind of see why I'm doing that. So once you have these blocks defined, you can move on to edges. Here I'm not using edges. Edges can be used to make arcs, kind of make circles, and kind of curve out geometry, which we won't touch up on this tutorial, but it's fairly simple. So here, boundary. So this is one of the biggest sections in our block mesh for this scenario. We're going to have an inlet, outlet, and walls, basically. So inlet is kind of what you would think. It's where everything flows in. And we're going to have 2 inlets because I defined the blocks here, the big rectangle on the left, as 2. So I can't just do a huge inlet of including both blocks. I have to separate them. So here I'm separating them into 2. So Openfoam knows that I want flow coming out of both of these. Walls, it's pretty much what you think. A wall that flow can't go through. So all of these have specific ways they have to be inputted, so I recommend that you're watching a video on how, it's pretty much the right-hand rule of how, because the order of these numbers are very important. So you have to keep track of vertices, keep track of where they are, and understand how you need to input them in to not get an error. Outlet, you only need 1 because it's coming out of a smaller rectangle, and that rectangle is its own block, so I'm only having 1 outlet. Center lines, just the bottom walls. Symmetry, because you want to have symmetry in the geometry. And front and back, I have 6 of them. Because this simulation is 2-dimensional, so I'm only looking at the cross section of these 2 rectangles. So I put all of the walls that are, there's 6 of them because there's 3 blocks, so 3 on this side and 3 on the other side at z equals -1 and 1. 6 walls to basically say it's empty, I don't really care, I want a 2-dimensional flow, so the Openfoam solver only solves for 2 dimensions. So this is basically block mesh, and I guess this is probably the hardest thing for a lot of beginners to understand how these vertices go together, the boundaries. So feel free to watch this again if it'll help you, but there's also a lot of tutorials on this. So moving on, control dictionary. So if I open this, you'll see the same top section, and you'll get to where you should start from. Start time. So it's pretty self-explanatory. Start time I want 0, t equals 0. And end time, how many seconds? So all this is in seconds. So this simulation is going to be short. I just want to, it achieves, steady state very quickly. So 0.2 seconds is fine, a delta t of 0.001. And all of these parameters, a right interval of 0.01, which means I gain the data, I write the data into a folder every 0.01. So you'll see here that all of these, the right precision, time precision, all these can affect what your result is. So please make sure to understand why these numbers were picked, and make sure not to make a mistake where it doesn't really solve the right way, because it's so easy to have an oscillating solver and have it go on forever or just give you the wrong values. So that goes right into FV solution and FV scheme. So if I open this one, these are a little more advanced, and these are pretty much the solvers on what you're going to be solving for in your simulation. So Gauss linear, a lot of these, if you pull up tutorials on it, it's pretty self-explanatory, and a lot of them use the same stuff. So you just have to make sure that whatever you're solving, you have the right right constants and right Gauss linear corrected linear. Make sure that the wrong setting. Solution is a little more intuitive. Here it shows the different parameters that I care about. So P, U, P final, U final, and all these show is the solver that I'm using and the tolerance. Now tolerance is super specific. So if I do a really, really low tolerance, it'll keep trying to find a better and better iteration that solves it, that less change per iteration. That's all iterations are. So a tolerance is when that change is that little, 1e to the negative 6, stop. So if you do a very low, it can actually not give you as accurate things, so you don't need anything more accurate. And that's all sig figs. If you've gone to have high school math classes and science classes, you understand significant figures. So make sure that for the tolerance, it's not too extreme where you have to wait a while for it to converge. For this case, 1e to the negative 6 is good, and it will produce just as good if you did 1e to the negative 8. You just don't have to wait as long. And for pimple, for the pimple solver, you have to define what parameters you want for the pimple solver or pimple foam. So all these you can look online, but these work for a contracting flow. So off 15, 1, 0, 0, 0, no. So once we get to here, we can go into a different folder. So that's for all system. Constant's pretty self-explanatory. It just pretty much gives a property. So we're using Newtonian fluids. So Newtonian fluids like water, air. Non-Newtonian is blood, and there's some other weird ones. There's some weird yeah. So there's some Newtonian fluids, some non-Newtonian, so you have to make sure that you have that right one. And nu, which is the kinematic viscosity. I'm going to be playing around with that later in the tutorial, but 1e to the negative 5 is pretty standard, so we're going to keep that. Turbulence properties, this is a little more advanced, but basically laminar, turbulent flow. Our simulation type's laminar, so our flow is going to be slow. It's around ½ meter per second for most of my simulations I'm going to show you today. But also the coefficients, a lot of these you can find online. I did not just make these up out of my head. I found the tutorial that I downloaded that based this off of has these numbers, so I did not change them. So now let's go into the constants. So now U is the most important to me. That's what we're trying to study here and look at in the simulations. What we're mostly concerned about is looking at the flow, looking at specific streamlines and seeing how the flow changes when this contraction happens. That's the goal of this. So right here, U inlet, which is just pretty much a variable, is defined as ½ meter per second in the x direction, and then 0, 0 in the y and z. So basically 1d flow. In these dimensions, you can look, this is meter, so 1 meter, and then per second. So meter per second just defines the unit. So meter per second. And inlet, I want to take that parameter. So I could have just probably put it right there, but I made it a variable. So once I have that variable, inlet is defined, outlet is at the start uniform, so those are 0, 0, 0, and at the wall, obviously 0, 0, 0. So I'm putting in ½ meter per second. What's going to happen? P and sigma are basically, I didn't really need to change them much. You do have the units again. I want 0, like I don't want a gradient. I don't want any change. I just want it to be static. I want to see how the velocity affects it. So all these are basically the same. You'll find them, and you don't have to worry about them. It's this as well. So once we have all these, we can begin to get it onto Openfoam. And to do that, I will get it into the terminal. So you can start from the terminal by going, command and getting into Openfoam, but an easier way is to go right to the folder and just open in blue CFD, which is my Openfoam. It kind of writes into it, gets into it, and now you can see that my directory is right at the folder that I want. So very simple. So first thing to do whenever you're running something is to mesh your geometry. So to do that, I'm just going to do a basic block mesh. And it's very quick because our geometry is fairly simple for the most part. So it was very quick. The long one to do is our next command, which is pimple foam. And that's the type of solver we're using. It's simple and piso combined. Pimple foam, I don't know who got the name. But it solves the incompressible flow in a large time step transient solver. So all I'm going to write, I have the block mesh already there. I'm going to write pimple foam, and it's going to start iterating. So each time it's iterating, trying to find the velocity at each time step. And if I actually go into, if I'm not too slow, you can see the folders being created at each time. It's going to end at point 2. So there we go. So I have all these folders now in flow contraction. That is the data for these variables. So you can see that use here. And if I open it, it's just a bunch of numbers. So props to computers, because it would take years to do that by hand. So now that we have that, a basic command that you'll learn or have already learned, parafoam. So just let's open the foam or pair view, and let's look at our geometry. So first thing you got to do is just press apply. Now apply shows the geometry, and you can start to see right now we are looking at pressure. So this isn't too important right now. But let's switch to velocity. So here you can see that there's the velocity of 0.5, probably on this base right here, 0.5 blue color. And you can see that it obviously gets much faster at the contraction. And that's a basic fluid dynamics property that's probably understood by most, like a fire hose. Say a fire hose, it has a nozzle, it decreases the cross-section area, increases flow speed. That's why you can see people get out of control in the fire hoses, because it gets so fast, so much momentum. So now, once we have this, we can look at some interesting stuff. So I am going to apply a filter. So there's a lot of quick filters here, and the most interesting one to look at for this 2D sketch, 2D geometry, is glyph. So I'm going to click on glyph, and it's going to give me these different properties. Now if I press apply, I'll show you. There are big arrows everywhere. It doesn't show me a lot. So I am going to slide this bar down, get these arrows smaller so that you kind of can see. And here we go. So right here you can see that there is pretty laminar linear flow, so just going in pretty straight. Now once you hit around right here, you can see these arrows start to move. Now if you took any kind of fluid dynamics class, you can see that water always wants to go radially, so it doesn't take sharp curves, sharp turns. It does a radial formation, so you can see that the water hitting this wall, it doesn't hit it and then bounce off. It creates this steady state condition. Now if I press play, you can see that it actually figures out the steady state and kind of converges on it right there. So here you can see that the water comes in, or any fluid. The fluid comes in and turns in a radial direction and contracts, and then gets pretty steady and straight right here. So this is one of the first simulations, and it's kind of interesting to see how this flow behaves in just such a contraction. Now I'm going to X out of this real quick, and X out of this, and we're going to go back to the tutorial folder that I made, and let's look at some different stuff. So as I said, the kinematic viscosity, which is a high nu. So I have high and lows, and I already ran the block mesh simple pimple foam just so we didn't have to wait around and watch it go. So I'm just going to open the terminal, and once it's set up, sometimes it lags a little bit. Cancel out of that. Open this up. There we go. And I'm going to type parafoam. Apply. So this is a high kinematic viscosity. Now I'm going to do the same thing that we did last time. Glyph. Let's make them smaller because we don't want those huge arrows. And if I play, look at these arrows. Now this is actually kind of interesting. It shows a kind of phenomenon that happens in this corner. You can see that the arrows, they don't really figure out what they want, and they're going in a weird direction. It's not what you would think it would be. So with high kinematic viscosities, you see kind of a circulation area where it's coming back and forth, and if I ran it for longer, you could see that maybe they keep changing direction. So conversely, let's go into the low kinematic viscosity, and this might enlighten you in some of the differences between low and high kinematic viscosity. So here, parafoam, same thing. I'm going to apply. And right here you can already tell that there was more red on the low kinematic viscosity, but let's go look real quick. I don't want to give anything away. So, boom, shorten these arrows, apply. So here there isn't that error. So what this kind of, see, it stays right there. What this kind of shows us is low kinematic viscosity, that it's going further in. It doesn't have that fluidity where it's just, it can ramble around and make a circulation area right here. No, it's going to go right in a radial direction and converge into this contraction area. And this is, I think, 4 inches to 1 inch, just for understanding. And that actually brings me to something I might have forgotten to tell you. If I go back into this folder and go into System, now I'm going into Block Mesh Dict, which defines the geometry. Right there. If it's 1, it's meters, so every number is meters. Now I did a 0.0254 because that is a basic conversion from meter to inch. So all of these are now just in inches. So if I had this as 1, this would be a huge geometry, it'd be meters long. It's just 10 inches. So always pay attention to convert to meters and make sure you always have that aligned for all the different values. So now let's go into something else. So you saw the difference between high nu and low nu, or high kinematic viscosity low. Now I want to go into a 3D. So that was a 2D, so you can pretty much see just a cross section what it looks like. 3D is a little more in depth, and I'm going to go into 3D better actually. And let's do open. So with this, we don't really have a defined boundary layer, so it's fairly small. So even in 3D, it's kind of just the same cross section. I'll show you. Oh, not Openfoam, it's Parafoam. Common mistake. So I'm going to open, and this was solved 3-dimensionally, and I'm going to go into U, and you can see that with the 3-dimensional thing where I took off, you know how I had the empties to make it 2D? I made those just simply walls. So now you can kind of get a cross-sectional view on the flow. And it's kind of interesting how, you know, it's going around, I'd say 1 goes to 1.1 and goes to around 0.6. So and you can see on the other side it's basically all 0.5 because that's the inlet condition. So if I went to glyph and I did apply, you can still see those same arrows, but I'm mostly focused on right here. So with 3D, I'm not a master yet, but you can do 3-dimensional flows. It's just playing with the empty front and back condition. So another thing is bigger contraction. So there will be a limit where the laminar flow won't be seen anymore. If I have such a huge contraction, I have the same inlet speed, it might not solve it. Pimple foam won't be able to do it because it's thinking that, no, it's a time step transient solver, incompressible flow, this would not be possible. We cannot solve it. So it stopped me, and it has stopped me. Now, I chose a contraction with the same inlet speed of 0.5 meter per second that still worked, and that is this. So if I play this and then I go, you can see that speed going really quick. And then let's do U, boom, and let's do a glyph to look at these. You can see that's getting a little more chaotic. Now, fluids is super complex, so whatever experience level you are, you know, you should understand that there's not really a perfect way to solve anything. All this has error, and with error comes wrongdoing, so you have to make sure that you're not having too much error where whatever thing you're designing, engineering, it's not going to mess up because of your simulation. So you have to make sure that the conditions that you're giving it is correct for the type of solver you're using. And it's pretty obvious that I don't know if I trust this because it's starting to get a little more chaotic. I don't think pimple foam can really solve this. But it does show that, hey, as you increase the or decrease the contraction and make it a smaller contraction area, flows can speed up. And with flows speed up, they can become turbulent, they can be compressible, and it can cause a lot of error. So with that bigger contraction can come error. So now I'm going to show you changing the geometry up. I don't want it to hit a flat face. Let's do an incline. So this one's just a regular small incline, and we'll see how that affects the behavior of speed of the fluid and just the overall vectors. So apply, there. So basically what I did here into the control deck, which I can actually show you. Let's go right in here, system. So instead of having just pretty much square geometries, I increased this value and this value to 2. Now to do that, it just basically moves that up an inch, creates that geometry up an inch, so over those 10 inches, it climbs 1 inch, which is 6 or 7 degrees incline. So now once we have this, I'm going to look at the, oops, lights came on. I'm going to look at the vectors. So let's go right here, and right here. Gotta wave my hand to get some light. There we go. So now this is a little more interesting. now with this incline, it's not as much a flat face here. So you can see that it curves in, and this is all medium viscosity, so it is curving in, and it is going towards and becoming laminar. And as it kind of converges like a nozzle, a straight incline, it goes right and gets faster and faster, 2.2. And it starts at around, looks like 0.5. So this contraction, can be, this is how a lot of flow is speed up. This is how rocket engines work, just contraction and expansion. Obviously, it's huge, very hot gas. It's compressible, not the same thing because it's incompressible flow. But same kind of concept of increasing flow with decreasing cross-sectional area, flow speed. So let's go and look at a little more extreme version. So I'm going to go right into here. This tutorial for large incline. Let's look at that. So I'm going to open the blue CFD. And all this might look a little different if you installed Openfoam differently. I had to do it kind of a different way because I had Windows and I did not want to get Ubuntu. So apply this. Let's look at the same stuff here. So I'm going to switch it to U. I'm interested in U. I'm not really interested in P. Apply. So I'm going to make them a little smaller. Oh, too small. Very delicate. So I pretty much matched it up, and I left a little because I wanted to see what would happen at this small section right here. But you can see it's much easier to contract. So it actually kind of causes issues here. You can see that it should be pretty steady here. It should be pretty laminar and just going straight through. But it's actually kind of messing up. And it might be because it's just not a perfect solver or the geometry was kind of weird, but the basic idea is that the flow does contract slowly and it can get faster and faster to the same 2.2 because it's the same ending diameter, so it'll have the same speed as last simulation. But much gradual decrease in cross-sectional area, which leads to a gradual increase in speed. So, and you're definitely not losing a lot of momentum to the wall. It's kind of more linear, and if any kind of design, if you want to get to this end speed, yeah, you want to start with a gradual cross-sectional area decrease, not just a flat face. Water does not like flat faces. Any flow does not like flat faces. So lastly, I want to talk about fine mesh. And obviously, mesh is how close each calculation is to another. So the finer the mesh, the more accurate it can be, but also it can be your doom. Because if you have a very fine mesh where it's not necessary, it can escalate the amount of error very, very quickly. So with this fine mesh, let's go into it and just show you a little bit on what I changed. So here, the blocks with these numbers after these, this is how many cells in that direction. So obviously in my X, it's the biggest. It's negative 10 to 10. So I gave 75 cells for that. And here it's around 0 to 4, so I gave 25 and 1. Before it was like 25, 10, and 1, everything that we've been running. So 75, 25, and 1 increases the time it takes for pimple foam to solve by a factor of 3 or 4. So it took 2 or 3 minutes to solve this, which is much longer. So with any simulation, finer mesh can help, but it needs to be done right. And it also can take a lot of time. If I increase the amount of cells by 10, the time would increase by 10. So that's basically why we keep having to make sure that, yeah, this is a fine enough mesh where we still get accurate results. So you have to understand that. That's part of the engineer's job, is to understand how fine does it have to be accurate enough. So I'm going to go back to this folder and open it up. Oh, that might have already been it, but let's do it again. And type in parafoam. Apply. So to me, this already looks finer because I've been working with this a while, but an obvious way to figure out that it is finer is to go and let's look at those vectors again. A lot more of them. So that means each arrow was a specific a cell, a vector. So a lot more of them. So you can see that all this flow is coming in. It's doing that radial convergence, converging into the smaller area, and then you can see it speed up and basically get pretty straight around right here. But you can still see those angles here. So yeah, with a finer mesh, it can be more accurate, and I also can show you a little more of where each flow is, because if I had, say, a tenth of these, I might not even have a vector here. So it might make sense to have a lot more vectors just to see at every spot in this geometry what direction is the fluid going. So that's basically a finer mesh can create that and can let the engineer or whoever's doing it see it. So that was the basic tutorial of this. So I will also be sure to attach my work just so you can take a look at it. But with any of this, just make sure you start with something that works and change just one little thing, see if it works. It's fairly simple to run it and see if it worked, you can pop any errors. And just go from there. Always start with something that works. So if you're a new person, make sure that you're grabbing some tutorials that Openfoam has is very useful. But what's useful is going and doing it on your own. So with this, I was changing a lot of the parameters, seeing how it affected the flow. That's how you learn. So make sure that you're going to be doing that. And this tutorial kind of goes through what you see when you do that. So thanks for watching, and I hope you enjoyed it, and I hope it helps you learn Openfoam.